Thanks for the intro, Stephen. Hello, everyone. Delighted to be here today presenting to you. Even better that I'm actually here and we're not all sat in our spare rooms and bedrooms and living rooms, etc. on Teams. It's really great to see everybody in person. At the start of the Industrial Revolution, a lesser-known Scot, James Watt, became obsessed with making steam engines more efficient. Why was this? Well, Watt realised that if an engine was more efficient, it could go faster, drive more machinery, carry more passengers, it would be cheaper to run, use less coal, and although he didn't actually realise it at the time, it would actually reduce the carbon footprint and be greener. So what he did was to evolve the steam engine to make it more efficient, faster, cheaper, and greener. And I find it incredible today that almost 150 years later, we celebrate the innovation of Watt through electricity. And how fitting is it then that we find ourselves in Scotland today to discuss how the electrification of Scotland's railway, and hopefully England's, can be undertaken faster and cheaper to make the country greener. And that once again, Scotland is leading the way with the decarbonisation of its railways, with a target set by the Scottish Government to decarbonise the railway by 2035. As an industry, we need to meet the challenge of our politicians, as Bill mentioned this morning. And to do this, we will need another Watt evolution. If we need a Watt evolution, we need to be guided by science. We all know Watt's law, power equals voltage multiplied by current. But have any of us really thought about this hard? If we open our thinking a bit wider and explore charge, we can rearrange this equation using Ohm's law, and when we do this, the rate of work is equal to the potential to overcome resistance. Sound familiar? The decarbonisation of Scotland's railway by 2035 can only happen if the potential of all of us in this room can overcome the resistance of Transport Scotland and the Scottish Government to provide the actual funding. And to do this, we need Mott's law. Funding is the product of vision and politics. So for the next 10-15 minutes, I'm going to explore how we can improve the vision to create a greener railway for Scotland by winning the hearts and minds of the politicians, by showing them how we can deliver faster and cheaper. As an engineer, I always think we need to understand the first principles if we're truly to make a difference. If we explore the vision to decarbonise Scotland's railway by 2035, what does this really mean? Well, in terms of the ORR, they've stated a 25% reduction in CO2 emissions, which is generally measured at the exhaust pipe on trains. So we could just shift the problem somewhere else. In terms of Network Rail, they've got science-based targets for a low emissions railway. This goes a bit further and states that they'd like to limit emissions from their own operations to a 1.5 degree warming scenario. We also have terms like carbon neutral, but what does this really mean? Well, it gets you thinking and it gets you measuring, which is no bad thing. I'm a big believer in what gets measured gets improved. It's the basis of all good engineering. So while we're offsetting and relying usually on somebody else planting trees at the time that we're trying to use less power, and it's this final bit that is the key, using less power. Because when we get to net zero, the less power you need, the easier it will be. Now, net zero doesn't necessarily mean you can't use any carbon. The scientific definition in the Climate Change Act 2008 is that all 6 greenhouse gases are at least lower than 8% of the 1990 baseline. The reduction in emissions of greenhouse gases isn't just important for the climate emergency, it also provides us all with cleaner air in our towns and cities, which is a very, very tangible benefit of improved health and well-being for all of us. In Scotland, we've got local legislation backed up by the Transport Scotland Rail Services Decarbonisation Action Plan, published in 2020, and it demonstrates the understanding that an electrified railway is the best solution to using less power. So it's for these reasons of first principles that I absolutely agree that the electrification of Scotland's railway is the best way for the railway to play its part in averting the climate emergency. We can see here the demand for rail services over the last 70 years. The number of passenger journeys has more than doubled from privatisation to the beginning of COVID, and you can see the dramatic drop since March 2020 when COVID started. but signs of recovery are here already, certainly if my train to Scotland yesterday is anything to go by. And rail use will continue to grow as the modal shift takes hold that we talked about this morning, and we also start to recover and continue to recover from the COVID pandemic. In order to reduce the greenhouse gas emissions at the same time as rail use increases, we need to do more for less. So we need to think about the railway as an entire system, not just the engineering that goes into construction, but the holistic rail system, the rolling stock and the timetable. And this is why vertical integration of track and train under a single guiding mind is so important. The long-term vision for Transport Scotland is to use electrification for the vast majority of services, with only the most remote and infrequently used lines making use of alternate traction, as Bill discussed this morning. As we're still at the early stages of development of hydrogen and battery trains with bimodes to facilitate decarbonisation in the short to medium term, this appears realistic, but if we again turn to science, we can demonstrate that even bimode trains will never be as effective as pure electric trains. If we consider how far each train can get on a kilowatt of energy, we start to understand the long-term benefits of electrification from an entire rail system carbon cost perspective. Starting with hydrogen, this is an energy-hungry fuel to produce. The argument is that we generate green hydrogen, but that green electricity that we use could be used far more efficiently in other ways. And we have the challenge of fuel tank size. Hydrogen fuel tanks need to be significantly larger than the equivalent diesel tanks. And this takes up valuable seating capacity on a train, and currently technology makes it unviable for heavy freight trains. By limiting the fuel tank to an economic scale, this limits the range of the rolling stock, and we get into a spiral with the laws of physics in terms of additional weight to carry more passengers and travel further. Another exciting emerging technology is battery-powered trains. Battery-powered trains aren't actually new. They've been around since at least the 1930s, but the disadvantages have prevented them from becoming a regular choice of traction. While the losses associated with the transfer of electricity into the battery are more efficient than producing hydrogen, batteries are heavy. So the further you want to go, or the more mountainous the terrain, and let's face it, Scotland's far from flat, the more heavy the batteries get. Anyone with a mobile phone or a laptop knows the problems with batteries, the heat produced and the degradation with age. In the course of 3 years, the battery life on my laptop at home has reduced from about 8 hours to a little over 2. And I'm sure that's a familiar story for anybody with a laptop and even a phone as well. Train batteries are exactly the same technology, and they suffer from the same problems. So when we calculate the power demand for a route, the specified new life of the battery will be significantly greater than is actually needed. And again, this adds to the dead weight to the train to be carried around for the life of the train. Now we get to bimodes, the Holy Grail, the answer to all our prayers, or are they? Are they the best of both worlds, or are they an unhealthy compromise that eats more power than is necessary? The upside of bimodes is the avoidance of uneconomical overhead line, which is a short-term win in terms of capital cost of installation, but is it the best for the planet? The major challenge with any bimode train is delivering the same performance as an electric train, but with the added weight of the onboard power source, which in addition, for most of its life, is being dragged around under wires. So it's doing nothing but wasting precious energy. I can see James Watt turning in his grave. So in the short term, it's economic to use bimodes as the country is connected, and this is why I like Transport Scotland's long-term vision for using bimodes as an interim solution. If we look graphically at how we use a kilowatt of green electricity, ignoring transmission losses and keeping this very simple, we can assume that a pure electric train converts 100% of its power into traction at the wheels and achieves 100% of the distance. Comparing this with hydrogen and not getting hung up on actual percentages, we see losses occur in production, in transportation and in the engine. Consequently, the percentage of that kilowatt left to move the train is quite low. With a pure battery train, we would incur some loss in charging and then discharging the battery, but the bigger challenge is the extra weight. Not only do the batteries take up space, which means less seat for passengers, but the additional tons of dead weight need to be carried around and dragged up hills, all of which uses power that's not then available for traction. With the bimode derivative, we incur a percentage of the losses associated with either the battery or the hydrogen, but we also incur the weight penalty. So even under wires, we're wasting energy to move mass. It stands to good reason that science-based targets should follow the evidence and move towards full overhead electrification. The only exception to this would be where, for a long return period, say 50 years, the embedded carbon cost of electrification would require such significant alterations to infrastructure that the added traction benefit is outweighed by the impact of construction. Typically, this will be in areas with low frequency, low occupancy trains. So again, I have to say, I think Transport Scotland's map for the long term gets this absolutely right. So having made the revelation that overhead electrification is the best answer, what else can we do to decarbonise the railway? Well, the next couple of slides analyses even some of the data we produced for the Borders line electrification between Edinburgh and Tweedbank, using our train performance modelling software. This wasn't actually in our brief, but the modelling software and the graphical outputs helped us to identify an opportunity. If we start by looking at the terrain, we all know that you need to do more work and use more power to push a train up a hill. And this slide shows the gradient profile of the Borders line. What we can then do is look at the train performance, the acceleration and the braking, within the permissible speed on the line to examine journey times. And on here, the blue line is the train performance and the brown is the permissible speed. Generally, the two align well, but you can spot a wasted opportunity where the red circle is, between Eskbank and Gorebridge, where potential savings could be made by reducing the permissible speed to 60 miles an hour with no impact on journey time. And this could reduce the maintenance on the track and bridges, reducing the cost of maintenance for a higher speed than is actually achievable. If we overlay gradient and train performance and look at both lines, or not, there we go, and look at both directions of travel, we can spot a bigger opportunity on the down line this is. So just zooming in on an area, again in the red circle, for a train that's travelling from right to left, the green line represents the uphill gradient, the dark blue line is the permissible speed, and the light blue is the train performance. And what we can see here is the train is travelling uphill at a steady speed, 85 miles an hour. It's then forced to brake for a reduction in permissible speed to 60 miles an hour over a bridge structure. Once past the bridge, the train then needs to accelerate back up to 85 miles an hour again, all while travelling uphill. How much power has just been wasted? Regardless of the traction type, whether it's batteries, hydrogen, OLE, diesel, or even steam, the increased power demand for doing that comes at an energy cost. If we upgraded the bridge, we could remove that speed restriction, and every train for the next 120 odd years would use less energy to get up that hill. And this is how we at Mott MacDonald can think differently to make the entire rail system greener and bring health benefits to the nation. So we've seen an example of how to make the entire rail system greener and bring health benefits to the nation by doing so. How do we rise to the challenge of cheaper and faster? Remember Mott's Law, funding is the product of vision and politics. We'll only achieve the funding for the green vision if we win over the hearts and minds of the politicians. So we as an industry need to deliver cheaper and we need to deliver faster. But how do we do that? Well, as designers, we have control over material quantities. We can bring recent innovations such as static frequency converters, which could reduce the cost of linking the railway to the national grid supply. And this could be particular benefit in some of the more remote parts of Scotland. But again, Scotland are ahead of the game here. There's a long-term plan, it's written, the sequence is well thought through, and the final supply layout is built up in a logical manner. In terms of bridges, a few speakers have talked about this already today. We've seen a lot of challenge from industry around electrical clearances, and touch wood, these are now relatively well understood, I hope. As engineers, our teams can use data captured by the new measurement train to check electrical gauge clearance for a variety of different scenarios in a matter of seconds. And a new approach to managing public safety allows us to significantly reduce the scope of parapet works required as well. By challenging design norms and historically accepted rules, as Gary talked about, we can optimise designs to reduce material quantities required. Less material means less to construct, less embedded carbon, and less cost. The challenge is to identify the minimum viable product needed to meet the project aims, and that way the true infrastructure cost of electrification can be measured, and that will allow us to bring down the STK value. As designers, it's essential that we collaborate and drive down the scope and volume of material that's needed to electrify a stretch of line. We all know that time is money, so it's only logical that faster and cheaper are joined at the hip. We've recently reviewed our OLE design process at Mott MacDonald to see how we can support the drive for efficient electrification by being faster and cheaper as designers. On our current projects in Scotland, we're using data-driven design, new types of survey data and iTwin models to not only reduce the cost of our designs, but to increase the production rate while focusing on quality. An increase in design quality should result in faster and more efficient construction and a better end product for our overall client, rail passengers. Data-driven design allows us to harness the power of the computers that we all use to design from first principles. Generic and simplified design charts and lookups are replaced with software tools that allow us to optimize wire run lengths, span lengths, mast heights, foundation depths, and other aspects of the design. Design automation allows us to produce our designs efficiently and react quickly when change occurs. And this enables us also to update our designs in real time to include as-built data while construction is in progress. By automating the repetitive, boring parts of the design, we can focus the design attention on the more complex parts, and this allows us to optimize the most important aspects of a scheme and add engineering value as we design. We're using RILAR survey data and context share survey data captured from drones and helicopters to reduce survey costs and times and improve safety by dramatically reducing track access required for surveys. And by publishing iTwin models, as Alan Kennedy talked about before lunch, we allow stakeholders to review and comment on designs throughout the design process and provide valuable input to us on the fly. The last item there on the slide, well, we haven't actually done this yet on a UK OLE project, but do we need drawings? We've got the technology to issue and use design models now, either in CAD or through iTwins, for example, but we're still stuck on the idea of providing actual drawings. Who wants to go first and award us a design contract that doesn't need drawings? For my last slide, I just want to share some green innovation with you. Our densified laminate timber overhead line support, which is developed with the architects firm Moxon, is currently developed as a prototype. Just to clarify, the image on the left there is computer generated, the one on the right is real. If you haven't seen it already, I've got a 1:5 scale model outside on our stand, so I encourage you to have a quick look. The structure's lightweight. It contains less steel, 74% less embedded carbon than any system currently available. It's got 70% fewer parts, which makes it faster to install and cheaper and safer to maintain. Most of all, visually, it's less intrusive, which is particularly important in the beautiful green countryside of Scotland. So, to sum up, let's work together to bring about the next evolution in the railway industry, and let's deliver electrification faster, cheaper, and greener. Thank you.